Next, we are going to see problem based on inverse Fourier transform. We are going to use inverse Fourier transform to find the function, original function f of x. Right? So first problem, find the inverse Fourier transform of f bar of p, which is equal to e power minus modulus p into y. So given f bar of p, which is equal to e power minus modulus p into y, that is equation number 1. We know inverse Fourier transform of f bar of p, which is equal to, which is given by f of x, which is equal to 1 by root 2 pi integral minus infinite to plus infinite f bar of p e power I px dp, that is equation number 2. Now in equation number 1 they have given f bar of p, which is equal to e power minus mod p. So we are going to replace mod p, right, by minus p and plus p, because we know that mod p, which is equal to p, if p is greater than or equal to 0, that is positive. If it is negative, it is minus p, right? P is less than 0. So we are going to use this idea in equation number 1. So using 3 in 1, we will get f bar of p, which is equal to e power minus instead of mod p, we are putting p when p is greater than or equal to 0. It is equal to e power minus p, we are putting when p is less than 0. So minus p into y, that is equal to, so e power minus py when p is greater than or equal to 0, and e power py when p is less than 0. Now the equation 2 we are going to split into two integral. So because there are two interval for f bar of p, one is p is greater than or equal to 0, that means 0 to plus infinite, and the other is p is less than 0, that means minus infinite to 0, right? So minus infinite to 0, f bar of p e power I px dp plus second interval 1 by root 2 pi integral 0 to infinite f bar of p e power I px dp. So we are going to substitute the values for f bar of p. So 1 by root 2 pi integral minus infinite to 0, in minus infinite to 0, that is p is less than 0, f bar of p is e power py. So e power py e power I px dp plus 1 by root 2 pi integral 0 to infinite, in p greater than or equal to 0, f bar of p is e power minus py, e power minus py e power I px dp. Now we are going to group the power of e, right? The integral 0 to infinite e power py plus I px. So p is common, take it outside, e power p into y plus ix dp plus 1 by root 2 pi integral 0 to infinite. So here we are going to take minus p outside, so e power minus p into y minus ix into dp. So 1 by root 2 pi, we know e power ax, right? E power ax or a plus b into x, which is nothing but e power a plus b into x by a plus b, right? Instead of a plus b, you are having y plus ix, right? So instead of x, you are having p. So using that formula, e power p y plus ix by y plus ix, lower limit 0, upper limit 0. Similarly, the second integral plus 1 by root 2 pi e power minus p y minus ix by y minus ix into minus 1, right? That is minus e power minus p into y minus ix by y minus ix, lower limit 0, upper limit infinite. 1 by root 2 pi, substituting the upper limit, e power 0 by y plus ix minus upper lower limit e power minus infinite by y plus ix. Similarly, in the second term, 1 by root 2 pi minus e power minus infinite upper limit y minus ix plus lower limit e power 0 by y minus ix, because you are having minus, so minus into minus plus, right? 1 by root 2 pi, so that is 1 e power 0 by y plus ix, e power minus infinite 0 plus 1 by root 2 pi. Similarly, e power minus infinite 0, e power 0 is 1 and plus 1 by y minus ix. 1 by root 2 pi, 1 by y plus ix plus 1 by y minus ix. 1 by root 2 pi, taking LCM y plus ix into y minus ix, cross multiplying y minus ix plus y plus ix. It is equal to 1 by root 2 pi, minus ix plus ix get cancelled, 2y by, so multiplying a minus b into a plus b formula, a square y square minus ix square, that is equal to 1 by root 2 pi 2y by y square. I square is minus 1, so minus into minus plus into x square. Therefore f of x is equal to root 2 divided by pi, so into y by y square plus x square, because 2 into root 2 get cancelled, so you will get root 2 in the numerator. That is why root 2 divided by pi, right? Y into y by y square plus x square. Thanks.